All right, let me share my screen. This is lecture 2 of the Information Theory course on ISSS. I am your instructor Sachin from the Indian Institute of Science. Okay, last lecture I gave an introduction to information theory, defined entropy, and gave some properties. So we saw that if there is a random variable x, this is last time. So, so what entropy is, if there is a random variable x, discrete, and it takes values from an alphabet script x, and the probability mass function p of x is the probability that x is equal to value small x, where small x belongs to the script x, and we define the entropy h of x to be um, minus summation of p of x log p of x over all values of x in the script x. And we also define log 0 to be 0, or rather we define 0 times log 0 to be 0, so that if there is some alphabet that occurs with probability 0, then it doesn't affect our entropy. And we saw a few examples. For a few minutes, I'll give you a little bit of motivation for defining the entropy in the way we do. Today we'll start with motivation for the entropy formula. This is not the exact derivation, the axiomatic derivation. This is just a bit of motivation. and we'll do joint entropy, relative entropy, or conditional entropy. Okay, so first we define entropy in terms of bits. So we could think of entropy as the number of bits that we use to represent the output of a random experiment. So if there are two outcomes, then there is a certain amount of uncertainty. If there are four outcomes, there is a larger amount of uncertainty. So that it depends on the number of outcomes. If we represent the outcomes using bits, then we could say if there are two outcomes, you can represent the outcome using one bit. Then the uncertainty you have is the value of the bit. There are four outcomes, you can represent those four outcomes using two bits, and your uncertainty will be in those two bits. As long as you know both the bits, then you will know the outcome. If you don't know any one of the bits, then there will be a certain amount of uncertainty in the outcome. So this is kind of a vague notion that you can think of yourself to understand what uncertainty is. So you could say that uncertainty of a source is the number of bits used to represent its output. Then you might think that if it's a very low probability output, then you could maybe not represent that particular output. So you will try to represent only those outputs which have a high probability of occurring. So in keeping this type of notion in mind, we define some quantity called L epsilon of P, which is the minimum of seeding of log of cardinality of A. A is a subset of script X such that P of A is greater or equal to 1 minus epsilon. So what exactly this means is consider a set of outcomes such the probability that any one of those outcomes occurs is greater than or equal to 1 minus epsilon, where epsilon is a random quantity that you choose. Usually it is used to refer to small numbers. Epsilon is a small number, so 1 minus epsilon would be a large number. So if the probability of a set is greater than or equal to 1 minus epsilon, you're saying it's a high probability set, and you will only represent the outcomes which are in a high probability set. But also, you don't really want to use too many bits to represent it. So what you'll do is you'll find all the high probability sets, and you'll take the high probability set with the least number of outcomes, and you will represent that particular only the outcomes in that particular set, and you will ignore all the rest of the outcomes. So the minimum number of bits you need to represent a high probability set is this L epsilon of P. So this would be the minimum number of bits required to represent a set of probability greater or equal to 1 minus epsilon. For example, if you have uh, an experiment with eight outcomes that you represent by 1, 2, 3, 4, 5, 6, 7, 8, then the entire thing you could represent with 3 bits if you wanted to represent all the outcomes. But suppose I give you the probability distribution half, 1/4, 1/8, 1/16, 1/64, 1/64, 1/64. And I tell you that I only care about sets which have a probability greater than 1 minus 1 over 16. So my epsilon is 6. This type of thing is something you would have seen in your calculus classes. So in calculus, when you're trying to find the limit, given an epsilon, you have to find a delta such that if your x is within delta of a certain point, then the function value will be within epsilon of the function value at that point. So you would have seen such type of things in limits and continuity. This is also similar to that. So given an epsilon, I'll try to find sets of outcomes whose probability is greater than or equal to 1 minus epsilon. And in this particular example, if I consider the set of first 4 outcomes, 1, 2, 3, 4, then the probability of this set is half plus a quarter plus an eighth plus a 16th, which is equal to, so these 4 outcomes together have a probability 1 over 16. So the probability of the rest of the outcomes is 1 minus 1 over 16, which is equal to 1 minus epsilon. So that is a set P of A whose probability is greater than or equal to 1 minus epsilon. So the number of bits you need to represent the outcomes of set A would be log A base 2, which is 2 bits. Now you do this for all sets which have a probability greater than your threshold and find out which of those sets needs the least number of bits to represent, and that will be your L epsilon of P. Next, but this doesn't give you a nice expression for what your L epsilon of P is. So it just says minimum of a particular set. So you have to go over all sets. So it doesn't give you a proper method to find it. So how do you form these sets of higher probability? How do you select the outcomes? It tells you nothing about that. So that would be the next theorem will tell you how you would go about a proper procedure to go about doing that. The theorem says that this quantity L epsilon of P is equal to ceiling of log of n epsilon of P, where this quantity n epsilon of P is defined as minimum of L such that P of I greater than equal to 1 minus epsilon, where I goes from 1 to L. So what this n epsilon of P quantity is, so you have a random variable with a set of outcomes and you have a probability distribution. You arrange the variables and the probabilities such that the ith largest value is Pi. So you arrange your probabilities in the descending order. So P of 1 is greater than or equal to P of 2, etc. P of k, where P of cardinality of script X. For example, in the previous example, we have already done that. So this has a priority half, then next smallest priority is 1/4, next smallest is 1/8, then 1/16th, then 1/64th. So you arrange those outcomes in the decreasing order of probability. Then one by one, iteratively, you add an outcome. You take a set, initially it's empty, then you add the first outcome. Check that probability. If that probability is greater than or equal to 1 minus epsilon, you stop. If it's not greater than or equal to 1 minus epsilon, you add the next variable, next outcome. So that is 2. If the sum of the now it's a set containing 1 and 2. So if the probability of that set, which is the probability of this probability plus the second probability, if that is greater than or equal to 1 minus epsilon, then you stop. Otherwise, you add the next outcome. So you arrange the probabilities in the decreasing order, and then you add enough terms from the probability distribution such that the total probability is greater than or equal to 1 minus epsilon. And as soon as you reach 1 minus epsilon or greater than 1 minus epsilon, you stop. So that will give you the minimum number of outcomes you need to have in a set so that it is a set of probability greater than or equal to 1 minus epsilon. And this quantity is called n epsilon or p. So this would be one of your A's in this L epsilon P definition. So L epsilon of P doesn't tell you how you have to select the set of high probability. So you can select outcomes randomly and then you might. So in this example, it turned out that it was easy to find this set. But if this probabilities were all jumbled, like different outcomes had different probabilities, half like this, then 1/64th, it was something like that, then you could pick and choose outcomes in a variety of ways to get a high probability set. And then you would have to find the set that contains the minimum number of outcomes among all the possible high probability sets. So instead of doing that, here what to do is you arrange the probabilities in the decreasing order, add enough terms so that you have a high probability set, and that is exactly that, and represent that using bits, and that will exactly give you the value of L epsilon p. You're following what I'm saying, right? Yeah. So you have to you'll pick the one which has the minimum number of outcomes. So you'll need the minimum number of bits to represent that set among all the high probability sets. So, but that you can pick these high probability sets in lots of ways. Uh, Depending on the probability distribution, there would be a lot of sets which have this high probability. And instead of doing that, this theorem gives you one particular method where you arrange the probabilities in descending order and you pick right from the beginning. One by one, you add the outcomes so that the probability will exceed 1 minus epsilon. And if you do that, whatever set you get, that is exactly the set which needs the minimum number of bits. That's what the theorem says. So, and the proof for that is So just by construction, this set, whatever we have here, this n epsilon of p, it is a set of high probability, right? So the sum of p of I is greater or equal to 1 minus epsilon. So all the outcomes that you picked will form a high probability set. So this n epsilon of p is one of the a's here, and this L epsilon of p is the minimum among all a's, all the set A. So this L epsilon of p is just by construction less than or equal to ceiling of n epsilon of p. That is straightforward. You understood that? Or, huh? If you want maximum, you can just arrange in ascending order, right? Instead of descending order, then iteratively keep adding until you get the uh, high probability set. Yeah. So just by this construction, L epsilon of p is less than or equal to ceiling of log n epsilon of p. Now I have to prove the other way also. If I prove that L epsilon of p is greater than or equal to this right side quantity, then that will mean both quantities are equal, and that will prove my theorem. So to prove that it is greater than or equal to, what I do is first I take any high probability set. Consider any high probability set that is a subset of the alphabet. So since it's a high probability set, the probability of A is greater than or equal to 1 minus epsilon. Now the probability of A is the sum of probabilities of all the outcomes in that set, right? So I could write that as Pi. I is 1 to cardinality of A. So all the outcomes in A I'm adding, that will be P of A. That is greater than or equal to 1 minus epsilon. Now I add, so this is the sum of a set of cardinality of A outcomes, right? If I replace this set by the sum of PIs, then the probability will be greater, right? Because these could be any set A could be any of the outcomes, but when I add the same number of outcomes, but from this descending order arranged set, the probability of the same number of outcomes obviously will be higher because these are all higher or equal to the outcomes here. So you could, it's obvious that the sum of same number of terms from some random set A is always less than or equal to sum of cardinality of a number of terms when you arrange it in descending order. Uh, but this, so what this means is, um, so here you are adding this in the definition of n epsilon of p, you are adding L terms, right? And by adding L terms, you got the probability greater than or equal to 1 minus epsilon. But n epsilon of p says it's the minimum number of terms. So L should be minimum. So when I'm adding cardinality of a number of terms, and this set has probability greater than or equal to 1 minus epsilon, then the number of terms that I added here should be greater than or equal to n epsilon of p, right, terms, right? Because this is the minimum number of terms I can add in this fashion by taking terms in ascending order and in descending order. But here I'm adding cardinality of A terms and I am getting a probability greater than or equal to 1 minus epsilon. That means the number of terms that I've added, cardinality of A, is less than or equal to n epsilon of P. So n epsilon of P is the least number of terms I could add in this descending order to get a high probability set. Now I added A terms and I got a high probability set. That means that my the number of terms that I added here is greater than or equal to, sorry, it should be the other way. This should be greater than or equal to n epsilon of p. Okay. Then what do you have from this? So from this, if we take a log on both sides, that would mean log A is greater than or equal to log of n epsilon of p. Then you take the ceiling of log A is greater than or equal to log of n epsilon of p. And this is true for any set A subset of X, which is a high probability set. So it's true for any set. That would mean it's also true for the minimal set that we choose when defining L epsilon of P, right? Because when we are defining L epsilon of P, we chose the smallest high probability set. But that is also a high probability set. This is over all high probability sets. So this ceiling of log n epsilon of p is less than or equal to ceiling of log a for any high probability set A. So it will also be less than or equal to ceiling of log A for the minimal high probability set. So that would mean that L epsilon of P is greater than or equal to ceiling of N epsilon of P. So this we got these two inequalities, and combining those two you will get that L epsilon of P is actually equal to log of N epsilon of P. So we started out saying that I will represent only high probability sets and I'll represent them with the same number of bits. So I defined what a high probability set is, and I defined a quantity L epsilon of p, which is the minimum number of bits that I would need to represent the smallest high probability set. Then I said just saying it's a high probability set doesn't give me a good way to actually calculate the value of L epsilon of p. So I said I'll give another way of systematically finding out the value of L epsilon of p. And the method of doing that is by arranging the probabilities in descending order, finding ceiling of log n epsilon of p, and that will give me L epsilon of p. At this point, we have a systematic way to find L epsilon of p. But in the end, even this is not very convenient, right? Because you have to arrange the probabilities. Uh, it you still it still depends on the probability distribution, and you have to sort it, then find the you have to add iteratively until you get a high probability set. So if there are a large number of terms, you might need to do a lot of iterations. Anyway, this still doesn't give you something. It doesn't feel enough. So we try to simplify this further by doing the following, right? So this is a kind of okay for us, but make this more. We can make this formula better in some sense. So you could kind of get rid of the impact of this epsilon on L epsilon of p. Um, so here you have to add all the terms until you get a set of probability 1 epsilon of 1 minus epsilon. That will also depend on epsilon. So this type of dependency you will try to isolate it. So the idea is consider all symbols that are more likely than a threshold. And this threshold is this way. So you consider the set A lambda, which is the set of all outcomes such that the probability of each outcome is greater than or equal to 2 power minus lambda. So here it's not, uh, this set is not based on the probability of the sum of all the outcomes in that set. Unlike the previous cases where you are looking at sets of outcomes such that the sum of all the outcomes was greater than some quantity. Here, instead of that, we'll just look at outcomes whose probability themselves is greater than or equal to some quantity. Or you could write this another way. You could write this as x such that minus log p of x less than or equal to lambda. Now we have a fact, which is that the log of the cardinality of this set is less than or equal to lambda. That's because the sum of probabilities of the outcomes in this set is less than or equal to 1, but each of these p of x's is greater or equal to 2 power minus lambda. So this is greater or equal to 2 power minus lambda x belong to, which is nothing but cardinality of a lambda times 2 power minus lambda. So from this, a cardinality of a lambda is less than or equal to 2 power lambda, and you take the log on both sides, you'll get log of mod a, the cardinality of a lambda is less than or equal to lambda. Okay. Now we have a theorem. If for lambda greater than 0, we have p of the set such that set of all x such that minus log p of x less than or equal to lambda is greater than or equal to 1 minus epsilon, then L epsilon of p is less than or equal to lambda. So this is a high probability set. I mean, we are saying if this is a high probability set, then the cardinality of that set is uh, a lambda, cardinality of a lambda. Log of that will be log of cardinality of a lambda. Since L epsilon of p by definition is the minimum number of bits, so the minimum will be lesser than or equal to lambda. It follows from this fact. So actually this, so in the definition of L epsilon of p, we had lots of high probability sets. If this set is one among them, then it will have log cardinality of a lambda number of bits to represent a lambda, but that will be greater than or equal to L epsilon of p, because L epsilon of p is the minimum among those. But this in turn, log a lambda is in turn less than or equal to lambda from the previous fact. So L epsilon of p is less than or equal to lambda if this is a high probability set. So now we have an inequality of this one, which you might have seen in uh, random processes, probability. So it's the form of Markov inequality. So we'll use Markov inequality. It says for a suppose x is a random variable which is non-negative, right? It's greater than or equal to 0. Then the probability that x is greater than a is less than or equal to expected value of x divided by a for all positive values of a. So that's the Markov inequality. And A proof, small proof for this Markov inequality is we have expected value of A is simply by definition sum of xi pi. Let's say x has a capital K number of x can take capital K number of values. By definition, expected value is uh, sum of the random variable value times the probability of that random variable value. So this you can split into two sums. The first sum is the set of all outcomes which are greater than a quantity A, and that I isolate by using an indicator function. So this indicator function will be equal to 1 if xi is greater than A, will be equal to 0 otherwise. So in this summation, you're summing all xi's, but whenever the xi is less than A, this term will go to 0, so that won't be added to that sum. So this entire sum is nothing but sum of xi pi for all xi greater than A plus sum of xi pi for all x less than or equal to A. So then that will give you sum of xi pi over all xi. Right? You could split the sum into two parts like this. And then since all these quantities, it's a non-negative random variable, right? So all the xi's are non-negative. Probabilities are also non-negative, and the indicator function is obviously non-negative. So if e of x is greater than the sum of two terms, or it's greater than this sum plus this sum, then it's obviously greater than any one of the sums. So that, for example, 7 is greater than 5 plus 1, so 7 will be greater than 1 and 7 will be greater than 5. So this expected value is greater than the first sum, I is equal to 1 to k, xi indicator xi greater than a pi, right? Which is again, so since all the xi's are greater than or equal to pi's, greater than or equal to a, the sum of xi pi will be greater than or equal to sum of a times pi. This is actually greater than, right? Because each xi is greater than each a. So if you replace xi by a in each of the terms in this sum, the entire sum will be greater. But this is nothing but a sum of all the probabilities such that xi is greater than a, which is nothing but the probability of the set x greater than a, right? So e of x is greater than a times p of x greater than a. We rearrange the terms, we'll get probability of this set p of the set such that x is greater than a is less than expected value of x divided by a. So that is the Markov's inequality. Now, if we compare this, what we have here, we have 1 minus epsilon on the RHS. So, and we also have greater than or equal to here. So, we'll convert this equation, Markov inequality, into that form. And to do that, let's say E of x over A is equal to epsilon. So that would change this equation to P of the event x is greater than 1 over epsilon E of x is less than epsilon. So then the complementary event will be the event x less than or equal to 1 minus epsilon E of x, right? The complementary event, if some event has probability less than epsilon, if it has a probability epsilon, the complement of that event will have a probability 1 minus epsilon. So if this event has probability less than epsilon, then its complement will have probability greater than or equal to 1 minus epsilon, right? So now we we have an inequality of the form P of some set is greater than or equal to 1 minus epsilon, where that set is set of all outcomes such that minus log P of x less than or equal to lambda. So yeah, I change this, right? So if this is the event, random variable x takes a value greater than the RHS. So the complement of that is the event that the random variable takes a value less than or equal to the RHS. Yeah. So then its probability will be greater than or equal to 1 minus epsilon. So now to get it into the form that we want, I can substitute lambda is equal to E of x over epsilon. And I can substitute in place of x uh, minus log p of x. So that will leave me with p of the set minus log p of x less than or equal to lambda uh, let me see. Okay, actually I can use this. I am actually going to use this directly. And in place of x, I'll replace that by minus log p of x. And in place of a, I will put epsilon. So I get p of minus log set of all x such that minus log p of x is greater than epsilon is less than e of minus log p of x over epsilon, which can be written as minus, okay, we'll keep that as it is. Yeah, it's the entropy we had, right? Yeah. So we had the entropy, but we still have to relate it to L epsilon of P, right? So L epsilon of P was less than or equal to um, lambda. So here what we got was by replacing lambda by sorry, give me a minute. Atta. Oh, nana cut kar. Oh, bye. Sorry, where was I? So this was P of less than or equal to lambda is greater than or equal to 1 minus epsilon. Okay. Wait. So here what we do is we will define a random variable z, which is the minus log p of x. So this equation then will become p of the event z less than or equal to lambda is greater than or equal to 1 minus epsilon. Okay. Then in this Markov inequality form, we will replace, since z is minus log p of x, which is log of 1 over p of x. P of x is between 0 and 1, so 1 over p of x will be quantity greater than 1. So the log of that will be a quantity which is a positive quantity. So p of x is greater than 1, log p of x, log 1 over p of x is uh, positive. So we can apply the Markov's inequality over z, right? Since z is a non-negative random variable. Now this is for any non-negative random variable x. So since z is equal to minus log p of x greater than or equal to 0, we can write that p of z less than or equal to e of um, z by epsilon greater than or equal to 1 minus epsilon. Then we choose the threshold lambda such that lambda is equal to e of z by epsilon. Okay. Then that will turn this to p of z less than or equal to lambda is greater than or equal to 1 minus epsilon. And now we have L epsilon of p less than or equal to lambda. So L epsilon of p is less than or equal to lambda, which is equal to E of z over epsilon. Right? So L epsilon of p is less than or equal to E of minus log p of x divided by epsilon. Did you follow that? Just writing the same thing in different ways, that's all. And in the Markov inequality, we are choosing. So here the threshold we can arbitrarily choose. Uh, and by choosing the non-negative random variable as minus log p of x and my lambda as e of z over epsilon, then I will get the probability of z less than or equal to lambda will be greater than or equal to 1 minus epsilon, which means that's a high probability set. And from that I get L epsilon of p less than or equal to lambda, which is equal to E of z over epsilon. So now we have this is not the exact formula, it's an upper bound, but still this upper bound is much more clearer than the previous formula that we had, which is n L epsilon of p is the ceiling of log n epsilon of p. So this isolates the effect of epsilon from the probability distribution. It won't be, it will be at least some fraction of L epsilon of P. That's what this says. So we can't really use it as a direct formula. We can't really say that this is the entropy because it follows this, right? So this actually started out as giving you a motivation for why we use a log in the entropy formula, where we kind of get the log from. So why we are interested in the first place, why we are interested in the expected value of the log of probabilities. Huh. Yeah, 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 yeah. So that is kind of the formal definition. This is only some vague motivation. This is something that one of my professors taught. That's why I'm teaching this to you. I don't think you'll find it in any textbook, uh, or maybe he referred to a different textbook, but it's not there in the reference textbook that I told you, Thomas Cover, or it's not there in the notes that I gave you also. Yeah, it's not there in Massey. So this is just some type of motivation to tell you why we would think of log in the first place. Okay, this probably won't be that useful to you any where other than just understanding this. That's all. Um, at least as far as all the textbook I have seen, they don't really mention this anywhere. Since my professor taught this, I thought I will also teach it to you. That's it. Since I didn't do the other derivation, right? Uh, this would serve as a little bit of motivation. Okay, now we'll move on from this to the. There won't be such sections in the rest of the course. Most of the thing will be from some textbook or notes or something like that. So we'll move on from this and we'll go to last time I gave properties of entropy and binary entropy function. I think I did. Now we'll go to joint entropy and conditional entropy. Also, this entire process that we did here, it's kind of good practice uh, while proving stuff. So we use a lot of things that would be typical in proofs. For example, we proved that some quantity is less than or equal to something else, some quantity is greater than or equal to something else, right? So a lot of proof techniques are used here. So it's good for that because the most of this course will be of the form I'll give you a theorem and then I'll prove something. I'll prove that theorem. And there will be few applications, not too many. Mostly coding and capacity of channel. but other than that, there won't be any applications here. Okay, so joint entropy, similar to how we define entropy, the joint entropy h of x comma y. So it's defined for a pair of discrete random variables. It's also defined for continuous random variables, where wherever there is a sum, you will represent it with an integral, and uh, there will be a differential dx dy corresponding to different entropies. So for a pair of discrete random variables x y with a joint distribution p of x comma y, the joint entropy h of x comma y is defined as follows: summation over all x in the alphabet and over all y in the alphabet for y, p of x comma y log p of x comma y. Or compactly, you can write this as minus expected value of log of p of x comma y. That's the joint entropy. So if two discrete random variables are distributed uh, by the probability mass according to the probability distribution function p of x comma y, then the conditional entropy will be defined as h of x, y given x, where by definition, so this is just notation, since y is a random variable that can take a lot of values and x is a random variable that can take a lot of values. So you're not really conditioning on one particular value of x. So it's the average over all values of x. So average of the conditional entropy of y given x is equal to some particular value x, where that quantity itself is defined as sum of p of y given x log of 1 over p of y given x. So even in your random process course or probability course, when you say probability of a random variable y given random variable x, it's not that well defined a quantity. So you can easily define what probability of y is equal to some value y given x is equal to some value x. Yes, you can define that, but probability of y is equal to y given a random variable x, this is not that easy to define. Doesn't of course you will find workarounds and find definitions for that, but it's not something that has a meaning that you can easily grasp. So in case of entropy, what it means is the entropy in random variable y given a random variable x means the average over all values that the random variable x can take of the conditional entropy of y given x is equal to a particular value. And that entropy itself is defined as sum of p of y given x log 1 of p of y given x. So this is a quantity that is easy to define. So it will come up in communication channels also. The transition probability. So if x is a vector or information vector that you send, and y is the information vector that you receive, then probability that you received a symbol y when a symbol x was sent will be defined for most channels. For a channel, when you say a channel, that quantity will be defined. So using that, it's easy to compute the conditional entropy. Now there is another way you could write this. You could take the p of x into the summation, and you could write summation over all x in script x, all y in script y, p of x times p of y given x. So that will be nothing but the joint probability p of x comma y. So log 1 over p of y given x. This you can write it as minus e, the expected value of log of p of y given x. So when you write something like this, you have to be careful to note that it is just a notation. So there's no such thing as a probability of a random variable given another random variable. Probability is defined only over events, and y given x is not an event. So it is a notation that means something else. So when you write it like this, what it actually means is you're averaging over all values x, y, and you're averaging the quantity log of p of the event y is equal to y, given the event x is equal to x, something like that. Okay. So here, if you so a remark is if these are independent random variables, that is, the joint probability distribution is equal to the product of the probabilities, individual probabilities. That is, pxy, the joint distribution of x comma y, is equal to p of x times py of y. So whenever it is obvious, we'll just drop it in the notation, but this is what it actually means. Um, this, if this holds, then we say that x and y are independent random variables. In that situation, what will happen is the probability of y given x will be nothing but the probability of y. So what will happen is h of y given x is simply the probability p of x, x belongs to script x, p of y log 1 over of p of y given x, y belongs to script y. Now this uh, and this is just p of y. P of y given x was just p of y. So this is nothing but p of x. You can see this is by definition h of y, and h of y does not depend on x. So you can take the h of y outside and write it as h of y summation p of x, x belongs to script x. And if you sum over all the outcomes in the alphabet, you will get a probability 1, right? Probability of the what do you call it? Sample space is 1. So this is nothing but h of y. So if x and y are independent random variables, the conditional entropy of y given x is nothing but the entropy of y. So that's one useful result. Yeah. Yes. Yes. Yeah, it will lead to something like that. So the probabilities are the probability of x y is probability of x times probability of y, right? From this. So since we are taking log in the entropy formula, we will get log of p of x comma y is equal to log p of x plus log p of y. So those will get separated out and you will get an addition that will lead to h of x plus h of y. Or you could, so next rule that we will use. So here all these quantities we are defining for a particular purpose. We are defining it so that we'll use it later uh, in the two scenarios, two problems that we need to solve. That is, what is the least compression or while doing source coding, and what is the uh, capacity of a channel. So all this will be used there. For now, one more useful result is the chain rule, where if you have two variables x and y, the entropy, joint entropy in x and y is nothing but the entropy in x plus the entropy in y given x. So that you can work it out yourself. It's also given in Massey, I think. Uh, I think they have given proof there. Yeah, here. Yeah, yeah, yeah. So you can prove from that that h of x y is h of x plus h of y given x. And then if you have a series of sequence of random variables x1, x2, all discrete, x and n random variables, you can use a similar argument. Uh, it's just that when you're proving all these things, you have to be careful over what you're summing over, right? So here you are summing over all x's, you are summing over all y's. This is defined over all xy. So as long as you're careful over what you're summing and how what terms you can take out of the summation, you can prove all these things quite easily. And you can extend this from two variables to n variables as h of x1 plus h of x2 up to xn given x1. Uh, this you can further write it as h of x1 plus h of x2 given x1 plus h of x3 up to xn given x1 x2, and you can keep on going like this. In the end you will be left with h of xi given xi minus 1 to x1 or x1 to xi minus 1 over all I is equal to 1 to n. So it's h of x1 plus h of x2 given x1 plus h of x3 given x1 x2 so on until you get h of xn given x1 to xn minus 1. So proof of this chain rule for two variables would be log of p of x comma y is log p of x plus log p of y over x. So you take the expectation or you sum, so it's summation over all y and all x, p of x comma y, log of p of x comma y, log of p of x comma y, which is nothing but log p of x minus log p of y given x. And so this it's marginal. So log p of x does not depend on y, so you can take that outside. You'll be left with summation over script x log p of x into summation of p of x comma y over all y. That is the marginal distribution of x. So you'll get summation over script x p of x log p of x plus this second sum is h of y given x, and the first sum will be h of x. So yeah, that's the chain rule, and there's a corollary. You can write h of x comma y given z is h of x given z plus h of y given x comma z. So in the chain rule, you introduced a conditioning. So you earlier you had h of x comma y is h of x plus h of y given x. You condition it, and the formula will still hold. So h of x comma y given z is h of x given z plus h of y given xz. And one thing to keep note of in mind always is that h of x given y need not be equal to h of y given x in general. It can be equal, but not for any two random variables. Okay, I'll finish this with one example of how we would calculate all these quantities we have studied till now. So you have xy with joint distribution as given below. So here I'll write the value of x, and here I'll write the value of y. So x can take four values, y can also take four values, and the joint distribution. So this entry is p of x is equal to 1, comma y is equal to 1. So it's p of 1, comma 1. So the second entry is p of 1, comma 2. Or since the top one is x, it's p of 2, comma 1. It's p of 3, comma 1, p of 4, comma 1. So this is the joint distribution. From that, you can find the marginal distribution. So marginal distribution over x is sum of columns. So p of x is equal to 1. If you want to find, you will sum over all values of y of p of y comma x is equal to 1. So you should have seen it in probability. So p of x is equal to 1 is the sum of all these terms. P of x is equal to 2 is the sum of these terms. So you get half. If you sum this, you'll get half, and 1/4, 1/8, and 1/8. Similarly, for y, it's the sum of rows. So probability of y is equal to 1 is the sum of all these entries. Probability of y is equal to 2 is the sum of these entries. So if you do that, you will get 1/4. So y's are uh, equally likely. Now from that you can calculate h of x as, from this you can calculate h of x, sum of p of x log 1 over p of x. You try it out yourself, you'll get 7 over 4, and h of y will be um, 4 times 1 over 4 log 1 over 1 over 4, so log 4, which is just 2 bits. Then you can also uh, so if you want to find the joint entropy, you could do sum of p of x comma y log p of um, log 1 over p of x comma y, but that will take more time. Instead of doing that, what you could do is first find the uh, conditional entropy h of x given y, which is nothing but I is equal to 1 to 4, probability of y is equal to I, h of x given y is equal to I. So you could write this as 1 over 4 h of half 1 over 4 1 over 8 1 over 8. So it's the entropy of x given y is equal to 1. And how you get that is, um, so y is equal to 1, when y is equal to 1, x has this kind of distribution, but the conditional distribution is also a probability distribution. So the sum of all the probabilities must be equal to 1. So you normalize it with some factor so that the sum will become 1. So here the sum is 1 over 32 plus 1 over 32 is 1 over 16 plus 1 over 16 will be 1 over 8 plus 1 over 8 is 1 over 4. So sum of all the probabilities in this row is 1 over 4. So if you divide all the terms by 1 over 4, the sum will become 1, right? So if you divide all the terms by 1 over 4, you will get the distribution half 1 over 4, 1 over 8, 1 over 8. That will be exactly the distribution of x given y is equal to 1. Or you could do it individually like this. You could use the formula, probability of x is equal to 1 given y is equal to 1 is probability of x is equal to 1 comma y is equal to 1 divided by probability of y is equal to 1. So this is the normalization. So this is nothing but 1 over 8 divided by p of y is equal to 1 is 1 over 4. So it's half. So I directly you can normalize it even without finding p of y is equal to 1. So similarly, you do it for all values of y. For y is equal to 2, you will get 1 over 4 times. You will get the distribution 1 over 4, 1 over 2, 1 over 8, 1 over 8. So you normalize the second row. Then you normalize the third row for y is equal to 3. You normalize the fourth row for y is equal to 1. Or y is equal to 4. So you get 1 over 4 h of this distribution plus 1 over 4 h of this distribution. And you do that, do it yourself, you will get h of x given y is 11 or 8 bits. Then you can find h of x comma y is, what is it? It is h of y plus h of x given y. So it is h of y was 2 bits, 2 plus h of x given y is 11 over 8. So it is 27 over 8 bits. So that would mean your h of y given x is h of x comma y minus h of x, right? Which is 27 over 8 minus h of x was 7 over 4 or 14 over 8. So it's 13 by 8 bits. So you find h of y given x in this way using this method. And if you find that, you should get 13 over 8 bits. So this, no matter which method you use, you should get the same answer. So that's one way you can check whether you have made any mistakes in your calculation. Yeah. Uh, I didn't get your question. How common is? Uh, so see, you could have entropy, such large entropies, but what happens is when you are dealing with such large scales, right? Most of the time, you'll just assume that some quantity is going very large. So if you want to get uh, so uh, if the entropy is what is it? It's the shortest average description length, right? So if you have very few outcomes of the experiment or very few random variables themselves, you won't need uh, too many bits to represent it. So it would mean that either the number of outcomes is going to be very large if you want your entropy to be greater than 100, or the number of random variables is going to be very large. So in such scenarios, most of the time you will analyze things asymptotically. So you'll assume that you have a sequence of random variables x1, x2, xn where n is going to infinity, or the number of outcomes is going to infinity, or it's going very large. So you'll do analysis of that type. In practical scenarios, if it goes to very large values like that, right, then you won't do it by hand. You'll anyway do it via software through a code, maybe a MATLAB code or something like that. Then you don't have to worry, right? As far as I know, in none of the applications, uh, I or my people in my lab, but my lab is on coding, is a coding theory lab. So I don't know what the people working on information theory deal with, whether they actually try to do simulations like that. But people I am working with won't really have to do such huge computations. Yeah, yeah, yeah. You usually won't see what in that type of situation. What will they will do is they will just cut it into blocks and then do it, right? You might have Uh, so if you have a sequence of data, what you'll do is you'll divide it into smaller blocks that are manageable and then encode the smaller blocks. You won't typically encode a large sequence as is, right? If it's so you might send a byte, right, at a time. So a byte might have 8 bits. It might have like 2 power 256, 2 power 8, which is 256 different possible values. So you might send that, or you might send 1024 values. At best, you'll do that. But if it's 1 gigabyte, you won't use one particular. You won't send it as is. You won't take that as your variable. You will usually split it into smaller variables. Yeah. So even when proving capacity and all, right, you actually, while proving it, you take a sequence of random variables where the uh, number of random variables is going to infinity. But when you're doing it in practice, nobody can actually use that. Even when Shannon proved his um, result, that one of the results says that if the rate of your code is less than the channel capacity, then there is, uh, if you are transmitting at a rate less than a channel capacity, then there is a way to ensure that you can get arbitrarily low error values, right? You can, but to do that, you need to have, you need to be able to use infinite length code words or very large code words. But nobody in practice actually can do that, and nobody does Shannon coding in practice. So that's why codes like turbo codes are very popular, because they get near the capacity that Shannon, near the rates that Shannon said, uh, without being such cumbersome codes. They are easy to code and decode, while also hitting code rates and um, transmission rates as much as possible. Yeah. So whenever we have very large values, at least when I'm teaching, we'll just take asymptotic values. We'll just say n goes to infinity or something like that. In practice, if it actually arises, then even then, um, unless you are designing the system yourself to compute these things, then you don't really care. You let the software do it. So it's similar to linear algebra. Have you taken a linear algebra course? So they will teach you Gaussian elimination there, right? For a system of linear equations. Yeah, there, whenever you are taught the concept of Gaussian elimination, all the matrices are very small, and the values are also quite neat, such that there won't be any practical aspects in that. But when you are actually using MATLAB for data science or something like that, all the matrices that you are dealing with are of the order of 1,000 by 1,000 or 10,000 by 10,000, something like that. Then, unless you are designing the system yourself, there's not much point in thinking how you can do that fast or how good you can do that. You will just end up using the software. You just need to know what exactly to do. That's all. Yeah. So the more efficient computation algorithms and all, there are actually Gaussian elimination. There will be further improvements on it, right? That will make large scale computations even simpler. But you don't study any of those in your actual course. So here also it's same. So if in case you have to use such things in real life, then you will have to take a more advanced course, or you will have to ask someone who is very knowledgeable in that particular area. We will be dealing with, if it's practical concrete examples, there'll be very small examples like this, just two random variables each taking four values, or we'll be dealing in an abstract sense with y1, y2, yn, n going to infinity. Okay, that's it for today's lecture. Next lecture, I'll keep it on Saturday. Is that fine? This timing is fine, right? Okay, from next week, I'll continue at the same time. So, I will, okay, I'll share. Okay, so, I am actually using my class notes where these notes were written by my professor. So if it's just sharing with you, I can share those notes. They're um, more organized. Yeah, but yeah, I'll share them to you directly. I can't share it in public because I don't own those notes. But just to you, it's fine. Okay, that's it. We'll meet next week. Good night. Good night.